Okay, so let's address the title. Interesting. Okay, so the first thing, you might be all thinking, okay, what the heck is this guy talking about? Did we break like what's happening? Why 1 + 1 = 3? Anyways, so what I want to talk about is double lens scintillation. It's in the context of scintillation and science, I swear. So the first thing that I want to sort of talk about is pulsars. And these are very dense neutron stars, and you're going to talk about them for a really long time, but the main thing that I just want you to know is that we can see their sort of emissions, because when they're aligned to us, they sort of have this lighthouse effect, and we can sort of see their pulse traveling. And well, people sort of have telescopes, and they have seen, okay, if you actually gather data about the intensity of the pulse as a function of frequency and time, you get this interesting interference pattern. And an even weirder thing happens when you take the Fourier transform of this thing and just plot what that gives. So once you go from this dynamic spectrum, which is just the intensity as a function of the frequency and time, you end up with this weird structure that resembles a parabola, and an even weirder inverted parabola. So it's okay, that's really weird. And okay, the plot sort of, well, okay, thickens a bit, because if you think about pulsars, well, if they have an emission and they sort of arrive at Earth, you also have the ISM, and at first sort of glance, you might think, oh, well, everything's sort of anisotropic, and maybe, you just get a lot of scattering there. Maybe everything is turbulent and disordered. But once you actually look at the images, as in if you actually were to have infinite resolution in the radio, and if you were to just, well, look into the night sky and sort of see where the pulsar is, you end up seeing a bunch of lines like this. So that's really bizarre. So you have this sort of mystery of, well, you have this arcs, and you also have these lines. So what's happening? So let me just tell you a bit of a story. Well, first things, so if you don't see this, which is what you would have had if you just had scattering all over the place. So if you sort of picture yourself at the Toronto waterfront, and say, for instance, if you imagine yourself to be as like Whaley and you're windsurfing, I'm not quite this how the story goes, but if you sort of stay out a bit late and then everything gets dark, you sort of say, oh, well, that's interesting. This light that is almost like a point source, kind of like a pulsar, has this interesting effect in that it's being lensed by the water, the water waves. So, once you actually look at what the sort of data looks like, it's like, that's something interesting. So then Whaley sort of put this picture of, okay, well, if you have some corrugated plasma sheets, and they can sort of source this scattering in this way at the wave crests, you can sort of start getting cool lensing effects, specifically, let's say in the sort of, just to give you a bit of perspective, sort of our distances to pulsars, well, these are order hundreds or 1,000 parsecs, and these structures might be like AU scales. So it's not too bad to treat them as kind of like a lens, like a source plane, just using the thin lens approximation. And if you have scattering, these wave crests, you kind of sort of see that they will behave as sort of lines. And if you just sort of source the scattering from these lines, you start getting, well, the interference pattern that is sort of sought after there. So, okay, here's what I mean. And this sort of looks like, well, a line. Specifically, if you were to sort of draw this three-dimensionally, and if you were to just look at where the light rays go, you start getting, well, resembling the data that you see, the dynamic spectrum, like the intensities of the pulse as a function of frequency and time. And if you look at the Fourier transform of that thing squared, you start getting these images that resemble those. And you also start getting, as you add more images, you start getting the inverted outputs. And that's no coincidence, because, the light is basically the electric field. And if you were to have access to that electric field, you basically have the ISM imparting a bit of a, well, you can think of this thing called the wave field as kind of like the impulse response function of the ISM versus the electric field. And so the main takeaway is that these structures that cause the lensing from corrugated plasma sheets seems to align pretty well with this picture of the parabola. It just rises naturally. And then you also get the inverted arcs from interference with each of these points. And so that's, once you actually look at the data and you look at what these structures look like, it seems that it resembles them pretty well. You see that you have a bunch of these parabolas, and some of these have the inverted arclets. In weak scintillation, you actually just get these kind of parabolas, nothing more. But once you look at the data a bit more, you start to see a bit more diffuse and blurry structures. Okay, well, these are not the parabolas that I was showing before, but it seems like, they still have a bit of a parabolic shape, but they're a lot more blurry. And for a good chunk of the data, well, you just see a bunch of diffuse nothing. You basically see a blob. So, okay, you have a model that seems to comply with the top data pretty well. And then you have more things going. So, one thing that I sort of glanced over is that this is sort of scattering that happens basically by a single plane. Like I'm saying, a single screen is sort of responsible for all of this scattering. And remember that this sort of scattering work sort of happens at the folds of these corrugated sheets. But so far, it's kind of assumed that these are almost basically independent. So if you add another screen, you just say, oh, well, the effect will just be, I'll just see another parabola there. But once you actually start to let these interact with each other, as in if you have, well, emissions from the pulsar that get lensed by the first screen and then go to the second one, you can have very interesting things happen. And since you have a lensing model, you can predict what these things do. So in particular here, I'm just showing, okay, if I have my main screen, the blue one here, the red one here, if I'm just sort of varying the orientations and the distances and also their relative speed, and I just plot what, if I just ray trace what the trajectories would be, as what I would call like the double scattered images. This is what I'm showing on the gray. And well, you start to get all sorts of different patterns once you actually plot and see what comes out. Okay, well, that's interesting. And one thing that you can just naturally get from this is a bunch of these double scattered images. They can sort of start resembling some things that we see in the data, especially when we see one arc that is maybe a bit more defined than whatever is in the middle, and maybe just a blurry mess could just be all interactions. And in fact, you can prove that all of these points, all of these interactions, can even be sort of as bright as your initial points, which is kind of counterintuitive when you think about it. How can something that is lensed 2 times and sort of, capped by its brightness, how can it be almost as bright as the other things that are sourced? Anyways, so you might say at this point, well, Diego, you basically just found a way to like add noise to your data, to your model. So one thing that we have been seeing is that, okay, once you sort of plot what the data looks like, but this time you're just varying the frequency, as in you're going from low to high, you see that sometimes these blobby messes, well, they just turn into parabolas again. And it's a bit more defined and more in line with the picture that, oh, maybe we do just have these structures that are sources of scattering. And that's something that you can also get by this model, just because sort of the number of images, interaction images, depends closely on your frequency and bending angles. Okay, but so far I've just shown you what it looks like when you just have blurry masses. But now let me give you another example. So we have seen that pulsar scintillation is actually pretty useful for determining orbital parameters. If you have a pulsar in a binary, you can determine its geometry or even pulsar distances. And you can start probing also sort of the ISM. So here's an example of a pulsar that is, well, we can see that the bow shock that is sort of there is being probed by the scintillation arcs that we see. And something that was kind of surprising is that once you look at this, it turns out that there's about 25 screens. So we're usually dealing with one or two, and out of nowhere we see, oh, there's 25. That's interesting. Why? And one of the sort of things that we have been looking at is, okay, well, I showed you that you can have blobby, blurry messes, but under certain conditions and parameters and orientations, you can actually start to get emergence. And you can get all of these points to sort of condense into a line that most, well, kind of starts resembling another one of these structures. And you could sort of start thinking, oh, well, that kind of looks like another lensing structure. So that if you had not known this a priori, you would have said, that's clearly another structure. Okay, but that's not the only way that you can source one of these extra lensing cases. So the other animation that I'm going to show you is in the case that if one of these screens starts just sort of decreasing in size, and you see sort of what the effects are on the interaction images. You can see that once you reduce down to almost a single fold, your arc is pretty well defined. So you start getting order out of your blobby mess. And the other thing that is kind of relevant for what I'm about to show is that if you also have this sort of single scattering source, and you're sort of moving, first you're moving towards the line of sight, and then you're moving away from the line of sight, we sort of see this, well, the image that is being sourced by the red screen. And you also see the interaction images with the gray. And the reason why this is relevant and why this sort of a prediction of these two lens scenarios is that you get a prediction for what this arc is. And if we sort of look at some data, we have something pretty similar to that. So you see that there's a passage of something that kind of a compact region of scattering, and it's coming in, coming in, coming in, and then it sort of goes through the line of sight, like this 0, 0 point, and then it starts doing really messy things, like really weird things, and then you have this arc that is pretty asymmetric, and then once it exits, or at least when we think it exits, it just returns back to normal. It's really weak. And what we think is happening is that we have this sort of model, and then you can sort of start making our prediction. So with this, with the data, we can sort of plot its wave field and compare it almost a one-to-one with the actual simulation. And well, here I'm just simulating with the blue what we think is happening with the sort of main screen, the one that is always at the bottom. And with the red point, that's sort of what we think is the passage of the feature. And these gray dots are just to resemble the interaction, like the actual, I guess, the third arc that you would have maybe thought you would be inferring. So then we see the feature come in, we see its images, and it seems to resemble before it sort of passes the line of sight pretty well. And then the passage through the line of sight, this is I think, the interesting thing. I don't know how clear it is, but once you actually look at the wave field, like the structure here, you start getting a lot of power here that is not, it's not related to your main arc parabola. And that seems to only happen on one side. So if you see, there's a lot of power of the blue parabola on one side, but out of nowhere, there seems to be a lot of power on the other side. So that seems to arise naturally from this double lens scattering, where you can just have sort of a preferential sort of region where you can see these images. So that's still a bit of a work in progress. But yeah, I'm doing fine. Okay, well, in any case, I'll just leave you all with it. Pulsar scintillation offers a unique probe into the ISM and can help you sort of learn things about the pulsar's geometry, if it's in a binary, or its distance. So scattering by a single anisotropic screen seems to fit the data pretty well. And once you add another screen, it seems to fit a good chunk of the remaining data. Yeah.
Any questions?
Where do these corrugated sheets of plasma come from?
I think that they are thought to come from intersections between magnetic fields. If you have different magnetic fields, they at some point have interfaces where the magnetic field lines run in different directions, and so you can start getting reconnection. And I think that's what might be sourcing the corrugation. Yeah.
So you said one sheet or one screen fits the data like pretty well, and the two fits it like really well. I like imagine like the more screens you add, it just doesn't really have much of an effect. You said one of them had like 25, and it's still like the model still work similar like 2 screens or so.
Yeah, so there's a bit of ambiguity about if those 25 screens are all real screens versus if one of them maybe could be just an interaction, like one of those where the parameters are just right to span, just, well, a bunch of double scattered images. So turns out that to actually know if this is the case, it's a bit more complex and involved, but it could be possible to fit those 35 screens into maybe just 5 screens. No, sorry, 6.
Your question?
Just one clarification. You sort of showed that basically why you get a line is that your screen has to be seen at grazing incidents. Right? That's the analogy of the Toronto skyline. So that also explains why normally you don't see that many, because the screen has to be really nicely aligned to your line of sight to even be able to see it. And sort of statistically, one can actually show that if there is one really nicely aligned, it will completely dominate over all the other ones. There's maybe you get a secondary one, but then the rest should be quite unimportant. So this one with the 20 screens is actually quite surprising in many ways.
Just to follow up on the previous question, have people tried to forward model this? Is that tractable, or are they just too many degeneracies?
Forward model.
Like in the sense, like you laid out a number of screens and you figure out how many screens there are just by modeling and putting into the data.
Yeah, that's what I've been doing. Yeah, so it depends on the system. Really seems like sometimes maybe even for the one with 25 screens, sometimes really the like double lens double lens interactions may not fit the data that well.
But there's also some where they look really simple where we have everything, where it's completely forward modelable. But there's just one star where that really works, I would say.
So that's, what do you learn if there really are like overlaps? Is that likely to just be a statistical fluctuation, or is there?
Well, people try to associate these screens, like in general, not just the 25 one, with actual structures. So that was one of the things that they associated, well, for these screens, which is sort of the actual interfaces of the dash. Other people try to associate it with some H1 regions, others with the John Nebula maybe. So you get all of these lensing, like parabolate, pretty generically. And then you can try to say, oh, well, if I have the structure that is located here, and I know that, like, this thing produced, well, I know from data, but there's a scintillation arc that also lies there. Well, maybe it's not coincidence, maybe they're associated. But what I'm trying to say here is mostly that, well, that's what people have been doing, but maybe, one could be misled, you know, to think that maybe there's an additional lensing structure.
Well, let's see, can you go again?